All right, let's just jump right in. Have you ever stopped and wondered why some things in the universe just happen? You know, a fire burns itself out, an ice cube melts in your drink, a drop of ink just spreads through water. It's like they're all on a one-way street. Well, today, we're going to figure out the hidden rules that are directing all this one-way traffic in nature.
I mean, seriously, think about it for a second. You can light a log, and it'll spontaneously turn into a pile of ash with a bunch of heat and smoke. But have you ever seen a pile of ash just magically suck in some smoke and heat and turn back into a log? Of course not. It's like nature has a favorite direction for things to go, and our mission today is to find out why.
And yeah, there's a scientific word for this whole phenomenon. When a process can happen all by itself without you having to constantly push it along, it's called a spontaneous process. Now, this isn't about how fast something happens. That's a whole other story. It's just about the fact that it can happen on its own.
So, how in the world do we solve this mystery? Well, we need a tool that can help us track the energy behind all these changes. And that tool, my friends, is called thermodynamics. It's basically the science of energy in motion. And it's what's going to let us predict which way that one-way street of nature is headed.
But before we can track that energy, we've got to know exactly what we're looking at. In science, really the first step is always to draw a line in the sand, to define what you're studying and separate it from, well, everything else. Okay, so here's the basic setup. The little piece of the universe that we're actually interested in, say our burning log, we call that the system. And everything else, the air in the room, the planet, the sun, distant galaxies, all of that is the surroundings. Simple enough, right? The system plus the surroundings equals the entire universe. Now, systems aren't all created equal. You've got an open system, kind of like a cup of coffee, which lets both heat and matter escape. Then there's a closed system, like a sealed water bottle. They can get warm or cold, but the water's not going anywhere. And finally, an isolated system, like a perfect thermos, which, in theory, exchanges nothing. Knowing these boundaries is going to be key.
So, what's our first big clue in this cosmic mystery? Well, a really natural idea is that things just want to settle down, you know? A ball rolls downhill, it ends up in a lower energy state. So maybe all spontaneous processes are just trying to lose energy. It makes sense, right?
In the world of chemistry, this energy content has a specific name. It's called enthalpy, and we represent it with delta H. Now, don't let the symbols freak you out. That little triangle, delta, just means change in. So if a process gives off heat, like our burning log, we call it exothermic. And its change in enthalpy, its delta H, is negative because it's losing energy.
And this chart here visualizes that idea perfectly. You start with your reactants, our log and oxygen, at a high energy level, the reaction happens, and the products, the ash and smoke, end up at a much lower energy level. And that extra energy, it gets released as heat. So it really seems like the main driving force is just this quest for lower energy. Case closed, right?
Whoa, not so fast. What about an ice cube melting on a warm day? That definitely happens spontaneously. But to melt, the ice has to absorb heat from its surroundings. It's actually gaining energy. It's going uphill on our energy chart. So our first simple theory is, well, it's broken. There has to be another piece to this puzzle.
And that brings us to our second and honestly much more profound clue. It's not just about energy. It turns out nature has this incredibly powerful tendency to move from order to disorder, from neat and tidy to messy.
And of course, scientists have a name for this measure of disorder. It's called entropy, or delta S. Basically, the more ways the particles in a system can be jumbled up and arranged, the higher its entropy. And as it turns out, the universe just loves high entropy. Okay, let's go back to our melting ice cube. In its solid form, all those water molecules are locked into a super neat, orderly crystal structure. That's a very low entropy state. But when it melts, bam! Those molecules break free, and now they can tumble and zoom around randomly in the liquid. That is a much, much higher entropy state, and the universe favors that increase in messiness.
So, now we've got the whole picture. There are two huge forces at play in every single thing that happens. There's the push to get to the lowest possible energy state, that's enthalpy, and there's the pull towards the greatest possible disorder, that's entropy. And sometimes they work together, but sometimes, like with our melting ice cube, they're in a cosmic tug of war. Which, of course, leads us to the ultimate question. When the drive for low energy and the drive for high disorder are in conflict, who wins?
Who gets the final say? How does nature decide which process gets the green light to go ahead?
Well, the answer comes from this absolutely brilliant concept that ties it all together. It's called Gibbs free energy, and you can think of it as the ultimate judge and jury for spontaneity. It weighs all the evidence from both enthalpy and entropy and delivers the final verdict.
And here it is, the elegant little equation that settles the score. The change in Gibbs free energy, delta G, equals the change in enthalpy, delta H, minus the temperature, T, times the change in entropy, delta S. It's the perfect formula for balancing energy against disorder.
And the whole thing boils down to this one simple, crucial rule. After you plug in the numbers for energy and disorder and temperature, if the final answer for delta G is negative, the process will happen spontaneously. If it's positive, it won't. And if it's zero, it's basically stuck in the middle. That's it. That is the secret to the universe.
And this table is basically our cheat sheet. It puts it all together. Just look at that top row. If a reaction releases heat and it increases disorder, well, that's a win-win. Delta G is always going to be negative. That process is good to go at any temperature. Now, where's our melting ice cube? Third row. It absorbs heat, which is a point against it, but it increases disorder, which is a point in its favor. And what does the chart tell us? That it's only spontaneous at high temperatures, exactly when that T times delta S term can overpower the delta H term. It perfectly explains why ice melts on a hot day but stays frozen in the freezer.
So, what have we learned here? Spontaneity isn't just about one simple thing. It's this beautiful cosmic balancing act that's constantly weighing the universe's tendency to settle down into low-energy states against its unstoppable, relentless march toward maximum chaos.
Ultimately, everything we've talked about is summed up by one of the most fundamental laws of all of physics, the second law of thermodynamics. And it says that for any spontaneous process, the total entropy, the total disorder of the entire universe must increase. No exceptions.
And that kind of leaves us with a final, pretty mind-bending thought to chew on. If every single spontaneous event that has ever happened, and every single one that ever will happen, is just pushing the universe toward a state of greater and greater messiness, what's the endgame here? What does it even mean for the cosmos to be marching unstoppably toward maximum disorder? Definitely something to think about.